Two quick announcements. So you guys will get this, but I think the people that aren't here might not get this. I've been having major computer issues lately. My computer crashed and it had to be rebooted like a couple weeks ago. And what I'm finding now is that my lectures, like when I go to, like last night I spent literally like 3 hours trying to get my computer and the video uploaded. And it would always get to like 9% done, and then my computer would like crash. And at about 10 o'clock last night, my computer no longer would start. Fortunately, this morning it's starting, but I'm a little bit nervous about whether this video lecture and the last lecture are even going to be able to get online. So I'm going to try to transfer it and do it on my computer here, but if this one and the last one aren't online, then that would be the sort of reason why. So hopefully I'll get that taken care of, but this is what we deal with sometimes when we try to use technology. All right, so with that, last week we talked a little bit about sort of Edmond degradations as a method for figuring out what a protein was. Right, and in terms of sequencing proteins, or say peptides, right? If you have a series of amino acids, right? Let's just say HO2C, amino acid 1, amino acid 2. Amino acid 3, amino acid 4, amino acid 5, and then NH2, right? If we sort of do the Edmond degradation, then effectively what's going to happen during this process is that you do just sort of formally Edmond degradation, right? Effectively what will happen is it will spit out amino acid, say 5 in this case, right, so we'll get something that will tell us, we'll get that sort of Ligation, right, which from the Ligation we can figure out what amino acid 5 is, and then we'll just sort of sequence this over and over and over again. And you can imagine that if you have a sort of, even on smaller peptides, this can be a rather laborious process, right? It's like you set up a reaction, purify the components that are generated through it, isolate, purify, sort of keep repeating in terms of sort of characterizing even what the components are coming off. Like, it can be a rather laborious process, and certainly impossible when you start to get to bigger peptides and, say, bigger, for example, proteins and so forth. So I thought it was just worth mentioning kind of what people do nowadays. I think mass spec in particular has served as a huge benefit for protein, and specifically protein sequences. In fact, it's gotten to the point where if you have the right machines, they're expensive, but if you're one of these sort of proteomic labs that has, they're called LC-MS instruments, it sort of becomes almost automated in terms of basically inject it on this machine, it gives you data, the data goes into an algorithm, and it spits out a protein sequence to you. So it's almost gotten to the point where it's automated. And so I thought it would be worth it to just sort of mention at least roughly how this happens, at least in principle. It's a little bit more complicated. But if you think about it, pretty much every amino acid that's out there, if you look through all the amino acids, they all have roughly a different mass, right? With the exception of sort of leucine and isoleucine. Those are probably the only two isomeric amino acids. So each amino acid sequence and segment is going to have its own specific mass, right? And so if you just think about a general system where you have a series of amino acids like this, what can happen in mass spec is that fragmentation patterns that emerge could effectively tell you kind of what you would have, right? And so if we think about some of the common ways in which fragmentation patterns take place. Right? If you remember, right, when we sort of bombard this with sort of electrons, right, what will happen is an electron will come in there, it's going to rip out sort of a pair of electrons, so generally an electron goes in, sort of grabs another electron on its way out to sort of get this two electron pairs. Formally what you get, right, is a sort of cationic system, right, that looks like something like this. And if you sort of remember, lone pairs in specific, and even carbonyls even more specifically, are fairly common for fragmenting. They're some of the more standard ones that fragment. And again, you can sort of draw a here. What will happen is you'll end up getting compounds such as this. Again, it's the positively charged one that you'll see. But what will effectively happen is if you bombard, say, for example, a molecule like this that we've seen here, right? Effectively, what's going to happen is pretty much every place where you have the sort of carbonyl, you're going to begin to start getting fragments here that are going to effectively tell you what that fragment is, right? So you're going to fragment the carbonyl here, right? And you'll get basically the mass minus water, or minus OH, right? You fragment it here, you're going to get the mass minus this component over here. So you'll get all of this mass here. It's basically associated with that. So you'll get a sort of series of these amino acid sequences. But you're not going to get individuals like in the Edmond degradation. What you're going to get, for example, is sets, right? You're going to get pretty much every combination that you could imagine of different groups, right? And then from within those groupings, like you might get the di or tripeptide sequences, right? Or even more so. And from that series of fragments that you get, you'll have effectively masses that could only be, right, a dipeptide or a tripeptide of a specific amino acid sequence. And from the collection of all of that data, again, there are effectively algorithms that you can do, higher computational powers that will effectively allow you to take all of that data and then give you a protein sequence. It goes a slightly step further. That's the sort of general idea. There's a second sort of confirmatory nature within that, which is a mass spec within the mass spec. So sort of MS analysis, which will break it down even further for you to help give better sort of understanding of this. But this is really the sort of state of the art for protein sequences. I have a friend who's now a postdoc out in Scripps, California, in one of the big organic chemistry proteomic labs, or chem bioproteomic labs, this guy named Ben Cravat. And when I start to talk to him about, and this is a lab that's extremely well equipped, right? They have these instruments, they have the money. I don't know exactly how much they cost, but let's say in CUNY, there isn't one anywhere in CUNY, as far as I know. That just sort of goes to show how expensive these instruments are. When you consider that an NMR costs probably $500,000, right? And then you start to think that we don't even have one of these instruments here, you can start to think about how much these might actually cost, right? So, extremely powerful technique, but there's pharmaceutical companies will certainly have these, and select very well-funded labs will also have these. These are the types of instruments that you would physically, and we do this for NMRs as well, you physically need to write a grant for that instrument for your program, right? So it's not like a component of a larger grant. It's like you write this grant, you tell people, I need this instrument for this research, and you have to convince them that you need probably millions of dollars, and it's going to sort of go in that route. So when you think about that, you recognize that there's very few of these, but when you do have this instrument, it can be really powerful, and people that do proteomics, it's often beneficial for them to pair with research groups that might have these types of capabilities, or sometimes you'll outsource it. Like there's companies that will have this, and you'll pay them for to basically test your sample for them. So you'll pay basically for service as well. So very, very expensive machines. But again, these sort of previous methods, you know, again, it's too laborious, and this is generally how people do it in the future. So as you can sort of imagine that, the fragments can then be sort of put together in order to sort of get that. So I thought this was worth sort of mentioning. The book, I think in chapter 14, the mass spec chapter, there is a brief mention of this in like one of those little square blurbs, like maybe 2 paragraphs worth, that sort of gives you a general sense about this, and you can sort of read up about it there. But again, I thought it was sort of worth mentioning. Okay? All right. Okay, so with the rest of the class, we're going to discuss really 2 things. This is how you would sequence proteins, and obviously you can clearly see that. Do we have a calculator on that? Someone up here? All right. Yeah, you can just get it out and be ready for when I ask for it. Now this sort of represents, right, egg degradation might be useful if you've got only a few peptides. Bigger instruments for bigger proteins and so forth. In terms of synthesis, it's a lot of the same type of stuff, right? So we thought previously, right, if you were to make, say, a tripeptide, right, you might take something like a benzyl, right, so here's just a tripeptide, right? And if, again, you're sort of to imagine making this compound, right? We'll just put the Bach over there for now, right? What you're going to do is you're going to start from this amino acid, right? And you're going to do that coupling, right, as we sort of discussed. Then what you're going to do is, say, for example, deprotect the Bach group over here, and then couple on another group, right? And then you're going to have to deprotect this group, and then you're going to have to deprotect this group. And so in total there, within this peptide, that was about, 1, 2, 3, 4, 5 reactions. Okay? And if you were to guess what a typical yield is for a reaction, right? Like you guys have done reactions, you'll occasionally have 120% yields, but obviously that's not real, right? The best yield that you generally will get is maybe you're super good. The sort of quantitative yields that you'll often hear about are really maybe 98%, right? We often will say greater than 98% because beyond that, in a standard organic chemistry lab, just to put things in perspective, like if somebody says a 75% yield, it's very rare that you're going to go out and get a 75% yield. You might get a 77% yield, you might get an 80% yield, you might get a 70% yield. So there's a lot of variability just in terms of human, right? But let's say that you're a really good synthetic chemist, right? And you get a 90% yield on all these reactions. All right, so I'm going to need your calculator. So that's going to be 90 times 0.9 times 0.9 times 0.9 times 0.9, 1, 2, 3, 4 times 0.9. So basically 0.9 to the fifth. So 53.1. Okay? Okay? That's if you are making a tripeptide. That's fine. 50. Right, so 59%. 59%? Right. Somewhere in the 50% ballpark is the sort of point here, where it's fine. Like, you start with a certain amount of moles of this compound, and after a series of sequences, you get half of that number of moles back. That's fine, right? However, once you start getting to peptides and proteins, you can begin to see that this is going to exacerbate itself. Let's say that, for example, you wanted to make a 20-mer, right? So now, this is a 3-peptide sequence. Let's say you wanted to make a 20-peptide sequence. Each of those would then involve a deprotection step, so really it would be 40 reactions, right? So if you say you wanted to make, for 20 peptides, or for 20 amino acid peptide, right? Which is by nowhere near even proteins at this point, right? We're still smaller compounds, right? And let's say we did the same thing, 90%, 0.9 to the roughly 40th. Can we do that? 0.014. So this is going to equal basically 1%. Okay, that's only going to 20, right? So you started with a certain amount of moles, and now you've got 1% that you started with of this compound. Now what that means, right, is in addition, each of those steps is going to be a chromatography perhaps, some aqueous wash, materials associated with a lot of these different things, right? Now even if the chemistry is perfect, if it's 99.999% perfect for the chemistry, right, you're always going to lose material somewhere. Like that yield, there's a certain element of mass recovery that comes along with that, right? The chemistry might be great, but you might not be great at actually getting your product out of there, right? There's that human element. And even if you're really good, once you start trying to make a 20 peptide sequence, that's going to be very difficult. In addition, think about the amount of time that something like this would take when you consider aqueous washes and everything else, right? And so, one of the ways that we have sort of overcome this, and in fact a Nobel Prize was awarded for this, was can you eliminate this sort of mass loss, right, that comes with all of those intermediate steps? Can you simplify the purification technique in a way that can sort of at least maximize your percent yield, say get 99.5% yield or something like that, you know, and again, increase your yields exponentially. And one of the ways that we do this is by doing effectively solid phase synthesis. And anytime you see sort of solid phase synthesis, oftentimes there's something that looks like, you'll see sort of some bead that looks like this. This is sort of a bead. And that bead is generally going to be some type of polymer. Okay? And we'll talk about polymers a little bit in maybe a couple weeks. But I'll sort of just tell you about the sort of Merrifield resin. Effectively what Merrifield did was one polymer that's pretty common that you might have heard of is polystyrene. Have you guys heard of polystyrene? Okay, so this is styrene, okay? Polystyrene is effectively a polymeric form of this. So if you can imagine and on and on and on, right? Such that you basically get these repeats of styrene into the very large macromolecular, maybe hundreds, maybe thousands. And so effectively what you have, right, is generally there's something that's going to sort of quench this over here. Right, is you might have something here that sort of traps it, but you'll have a series of one, two. Looks like everyone's going off the chalkboard, so apologies to the people watching at home. But effectively what this is a polymer where you have a certain number of these styrene units within there. So there's this repeat, and again, we'll talk about this polymer a little bit more down the road, but again, it's just a sort of repeat of these. Now, as we sort of saw from some of the protecting groups that we dealt with, one of the protecting groups that we often saw was benzyl protecting groups, right? And so if you can imagine, when you were doing this polymerization, if you had a certain percentage of, say, for example, hydroxyls in there, right? Or actually the Merrifield resin, I should say, is a chloride. Okay, if you can imagine if you had a certain amount of polystyrene chloride in there, then what you're going to get is you're going to get a polymer like this, where occasionally you're going to have, I think it's generally over here, right? But occasionally you'll get a molecule that'll have some number of chlorides within there. So it's going to be some mixture based upon the stoichiometry that you have. So you're going to have a polystyrene resin where occasionally on there you're going to have that sort of benzyl group. And so one of the ways that we can sort of show this let's say we have our polystyrene. With a series of chlorides. So again, there's going to be a whole bunch coming off this one bead, right? Now you have this chloride, and one of the things that you can do, right, is that you can take your amino acid and we'll protect it as a Bach, we'll protect the amine as a Bach group, right? What you can do is you can effectively couple this, so you can treat this with a base, effectively make that benzyl, right, benzyl ether or benzyl ester bond there. Right, and now you've got an amino acid on this resin. Okay. Then what you can begin to do, right, once you've put this on here and once you've reacted these together, now it's a bead. It's insoluble. It's a polymer. It's not going to be soluble in water. It's not going to be soluble really in anything, right? And so it's heterogeneous in the solution, right? It's not sort of all together per se. You've got lots of different things within there. But your compound is on the bead. So everything else you can just wash away. You can take that bead and just rinse it, right? And then what you can do is you can take this and treat this with trifluoroacetic acid, right? The bead's going to be in there. You're going to have the trifluoroacetic acid resin. Now you've got your free amine, right? Then you couple it to the other amino acid. Now here's one of the keys about that coupling step, is you don't care necessarily about the other amino acid that you have, so you can, because it's going to be really easy to get rid of. So people often use very high concentrations of that other amino acid. You can use excess of those other amino acids, for example. It's going to react with it. Again, then you can wash away that urea that we talked about that could be a problem from the DCC. You can wash away any excess unreacted amines, and then you can continue with this sequence. Okay? So it accelerates your washes significantly, right? Because now you're not doing an aqueous wash, you're just rinsing the compound. You're going to increase your overall mass recovery, right? Because it's stuck on that bead, you're not going to lose that material in terms of material transfer. And the other thing that it allows is it allows automation, right? When you have a bead, there are now things, and Professor Geronimo Navarra, in fact, has a, I think he's, does he have peptide synthesizer? I think he might, yes. Oh, yeah. Yeah. Well, it's going to be dependent upon the size of the bead. But yeah, I mean, I'm trying to think of what you guys might have seen that would be sort of similar. Maybe like a third the size. They depend in size, but they can range anywhere from the size of, say, for example, a pea to maybe a tenth the size of a pea, right? So they're going to range in size. So they're big enough that you can clearly see the bead with your eye. They may eventually look as small as something like sand, but you would be able to see them. Yeah. Oh, right. So this is one of the points, is that once you do this, right, at the very end, right, you have it on the bead, right? And this is one of the problems occasionally with peptide synthesis, is that the last step is HF. So the sort of standard way that people will cleave this is hydrofluoric acid. I don't know if you guys know about hydrofluoric acid. It's pretty nasty stuff. I remember when I was in grad school, there was I sort of took it literally. I think people were sort of making a reference to, this is just my gullibility, right? Was somebody said, oh, HF is so bad if you look in the, like what the if you get exposed to HF and you turn to the handbook of what you're supposed to do, it says administer morphine till you're dead, right? That was kind of like, because it literally like will eat away at your bones. That's like part of like how nasty it is. So I don't think it would actually say that, but I think I believed it for a little while. But anyway, yeah, so the cleavage would be sort of HF, and so people have looked for other alternative ways to put that on there, but that's at least the classic way for Merrifield resin. Okay. So one of the cool things, I guess we can talk, I wasn't planning about doing this, but you brought up a good question in terms of the size of the beads. As you can imagine, the size of the bead, right, is going to depend upon how much compounds you have in there, right? So one of the other advantages to solid-supported synthesis, aside from what we have sort of talked about here, is something that's also very powerful, right? And that's something called combinatorial chemistry. That I think was, I don't know, I wasn't actually planning on talking about this, but I think I will, because it's kind of cool. Right, so if you have a really big bead, right, where you can have, I mean, it doesn't matter, you know, combinatorial chemistry, so I'll make sort of 2 points real quick. Combinatorial chemistry is basically the idea is of, let's say you want to make let's say you want to test peptides, right, and you want to make a lot of peptides, right? And let's say the peptide sequences that you want are 5 peptides in length. If you think about the possible combinations, right, of say an amino acid, the possibilities right? If you think about the fact that each of these has as many as 20 natural sources, right? 20, 20, 20, 20. The number of possible peptides that you could generate, right, would be 20 to the 5th, right? I need a calculator. Unless somebody can do math in your head, yes. How does this what? How does this maximize the yield? You don't lose all that mass from the washes that I was talking about. It's all stuck on the bead. So you're not going to lose, a lot of times when you have lower yields, it's because your yields and your low yields are because of the fact that you've been handling the material. And when you're handling the material, right, you're doing things like, for example, aqueous extraction in solution phase, transferring that. This is all on a solid support. So say, for example, you leave that bead in a single reaction flask, and you just filter out the solvent, rinse it, filter out the solvent, rinse it, filter out the solvent. You haven't lost any of your material on that bead. That's actually not how they do it. They actually have more filter-based systems. But you don't move, your bead doesn't move anywhere. It stays in there. So you're just rinsing it. You just rinse it, and then, so you don't lose a lot of that mass elsewhere. So you could have, and my point earlier was you could have a reaction that's quantitative. You could have a reaction that's perfect. Every equivalent, every mole of this goes to every mole of this. But you're probably still not going to get a 100% yield, in essence. This will allow you to do that because you're not, this will allow you in principle to get 100% yield based upon what you initially get on that bead, because the technical aspect of it becomes much simpler. It also accelerates the process a lot quicker as well, so it also speeds things up as well. Okay? So, all right. So, 3 million plus. Okay? So that's a lot, right? But let's say, for example, that, just to put things in perspective, let's say you want a peptide that binds to, I don't know, maybe a peptide-based drug, right? You want a peptide that's going to serve some biological purpose. And your hypothesis is that if you have a peptide, there's probably some pentapeptide that will bind really well to something, and you want to just assess every single combination of these. That's a big number, right? But you can do that, and solid-supported synthesis will allow you to effectively make those 5 million compounds in fairly quick order time. And the way that you can do that, and perhaps one of the easiest ways to do this, is, and so this would be called combinatorial chemistry. So say, for example, you start with the 20 amino acids, right? You would start with this. You'd start with 20 of these. right? So you start with 20 of these, right? You'd couple it to 20 different amino acid 2s, right? Now you do that coupling, right? Now you have 400 possibilities. Right? Now you do that again with an additional 20 compounds. Now you've got 800, right? Then you do it again, and so you see that as it sort of, sorry, not 800, 8,000, right? And then you're going to keep going up and up and up until you get to whatever, 3 million plus. Now the practical nature of how this is done, if you were to have to do 100 reactions, or sorry, be doing 20 reactions, or say towards the end, 3 million reactions at a time in solution phase, you're just not going to be able to do that. Right? But this sort of approach actually can make it feasible. And based upon what was asked earlier, there's an approach that was actually pioneered by this guy named Stuart Schreiber at Harvard, and certainly some others, of this sort of one bead, one compound approach. So if every bead that you have, right, if say you have 4 million beads, right, what you can do is you can do this thing that's called split and pool. Okay? And what that would mean is that you have 20 reaction flasks. Right? And each of those reaction flasks would have a different amino acid. Okay? Each of those will have a different amino acid, right? Into each of those flasks, you would put every single combination, right? Or for starters, say for example, right, you have these different flasks. What you would do is you take the sort of polystyrene bead and you'd attach it right off the bat. So now you get a whole bunch of beads, and let's say in each of those pots you have, you know, whatever the math would come out to, say 100,000 or so beads in each of these. And again, the beads have a certain mass, you would just weigh them out and you would put them in there. Right? Then what would happen is when you're all done, you pool all of the molecules together. Now what you have is you have a mixture of all 20 of those amino acids. And you simply, without even worrying about it, you then separate them into 20 new flasks and run the amino acid peptide sequence again in those 20 flasks. You then pull them together and you split them up again. You pull them together, you split them apart. Now what you realize, and what you're probably standing there scratching your head is, well, that's not going to control and make sure that I get every single possible outcome, right? Because sometimes you're going to get repeats. You can't have no way to control. So if you wanted to control, you could do it in a more systematic way. But if you want to get up to something like 3 million compounds rather quickly, this is what you do. And so to be able to maximize the number of, say, for example, amino acids, or the potential to have these, you use like 10% more. So if you have 3 million beads, or you want 3 million different compounds, you might use 3.5 million beads. And the likelihood is that you would get like, I think it's like, you wouldn't get necessarily all of them, but you would get 95 or so percent. There's some statistics behind it, but you'll get at least 25% of those. And then from each of those beads, if they're big enough, there's enough on each of those beads where you can effectively put them into, say, for example, spread them all around, pull them out, cleave them, and then you'll have molecules to do, say, for example, biotesting. Yeah?
Yeah, so one more bead test. Is it 1 week per molecule or one?
Yeah, so each bead, right, because you're not going to get crosstalk from the beads. Once the molecule's on that bead, it has a specific amino acid sequence. You're just going to take that amino acid sequence, and it's going to go into that pot, and it would react with different compounds, right? So it would react with one compound to put on one group. That same bead would likely go into a different pot, which would then give it a different one. This sort of whole combination would effectively allow you to get this. But the whole point is that you would effectively do 20 times 20 times 20 times 20 times 20 effectively different reactions. So 100 different reactions, vessels, in essence. And what you would get out of it, right, is 3 million different compounds. So that's kind of the potential power of doing it in the bead. But yeah, that bead has to have enough material. It has to be a big enough bead where once you cleave from that individual bead, you have enough material to both figure out what it is, right, and to do the biotesting. Because generally what happens is you're not going to characterize all 3 million of those. Generally what they do is they have automated systems which will effectively spread them out onto plates and then they cleave them individually, and they'll take out from those plates and go right into biotesting. And then if they find a hit, then you'll go back to that well that it came from, and you'll basically take a mass spec of it, for example, and try to characterize what it was. So powerful stuff that you can do once you get things onto beads. Yeah. Yeah, no, that's a good point. I mean, it probably would for a certain extent. That chemistry's all been worked out, So, people know what to do, But I'm sure that was a problem that was initially being worked out, and it probably does degrade it to an extent. And oftentimes, if you want pure, like what I just talked about, you're not going to be going in with necessarily pure peptide sequences, right? You may have slight mixed, you might have parts where it maybe didn't get coupled, so maybe you've got a pentapeptide instead of a, what's that? Oh, yeah, no, not if you're trying to make 3 million, no. There's things that people can do. There's other little tricks, like people have put like DNA templates so that you can follow what's going to where and so forth, but yeah, no. Anyways, I just wanted to sort of illustrate very quickly what the power of doing things on solid phase can be. All right, so this is another side note based upon bead size. So if you've got smaller beads, it doesn't matter. You'll have a whole bunch of beads. But if you have bigger beads, one of the advantages of having a bigger bead is that you could do this one bead, one compound approach split pool, right? Because that one bead could have enough material on it to do your testing and so forth. Okay, now, this is sort of solid phase synthesis, but even so, when you're doing solid phase synthesis, what ends up happening is you get to a point in that sequence length, right? Or even just in terms of the numbers, right? Like, even if we're getting 99% yields, right? 99.99 to the 20th. Can we get a 0.99 to the 20th? All right, let's say we want to make an enzyme, right? An enzyme that's, say, 1,000 of these, right? That would be, say, for example, 2,000 different reactions. So it would be 0.99 to the 2,000. Times 10 to the negative 9. Okay, so we're at like 0.00009% yield if we're getting 99% yield on every reaction. So you cannot do solid phase synthesis and make enzymes. You can make peptides, but what you cannot do is you cannot make enzymes. However, if you can make molecules like a 20-mer peptide, one of the things that you can do is you can combine the individual 20 unit, right? So you might not be able to make a 20-mer, but what if you made 20 20-mers, right? So if you had 20 of those, now you might have a 400 amino acid length compound, right? So it might not be realistic to do iteratively, but if you make individual amino acids and then you want to couple them together, that could offer a solution, right? And this is what I want to talk to you guys about today, and this is part of what's going to be the Friedman lecture next fall, which is sort of native chemical ligation. Okay? So native chemical ligation. Right? So the question becomes, if you have an amino acid, if you have a peptide that's, say, 20, right? And let's say you want to couple this peptide to another 20 peptide unit compound. There's a lot of issues with this, right? To just cleave a 20-mer peptide off the bead, have it in solution phase. Take another 20-mer peptide and have it in solution phase. Even if you were to, say, protect the ends, like we did in terms of solid supported synthesis, the bens will protect this one afterwards, and leave this one, say, for example, on the Bach, and then couple those two together through DCC. That at least gets you up to the 40, which would have some advantages. But there's another problem of peptides when they start getting to these sort of longer lengths. And that's that you begin to decrease your yields on those DCC couplings, in part because you begin to get folding of the proteins. You can imagine as you start to get to much longer proteins, there's foldings that might begin to shield the reactive groups and so forth. And so what you need is you need a way to effectively allow the coupling of these components in both a very high-yielding fashion, preferably in a way that you could just do on two peptides where you don't have to worry about protecting groups, right? And do so in a way that you can get high yields, very high yields, and so forth. And so the sort of general way that people have done this and have sort of exploited this is to use a pretty neat reaction that's known with specifically cysteine. Okay? So if you have at the N-terminus if you took this molecule and you took carboxylic acid, and you tried to react these two together with DCC, the reaction would be horrible. But if you take this, and instead you have over here a thioester, okay? So you can imagine doing your chemistry from N to C, so you build off, and then before you cleave it, you put a thioester there, and then you cleave at the very end. So your peptide has, say, for example, a thioester there. If you take this thioester and you treat it to a molecule that has a sort of N-terminal cysteine, what will happen is these will actually react extremely well together. And what will happen is you will get you'll get extremely high, basically quantitative yield of these two. It will selectively react there, and again, it's going to allow you to basically start to build up from these components. Okay. So why does this work? What is the mechanism that forms? Why would it work, for example, in folding type sequences and so forth? Well, it turns out that the thiol and the exchange between thioesters, you have an ester, a thioester. The exchange and the ability to make other thioesters is a fairly quickly and fairly rapidly reversible process. So what happens in this process is that that cysteine, sorry, the thiol is going to attack and basically make a new thioester bond. Now, why do you think this would react much faster than this one? What are some of the components that we know about nucleophilicity that might allow this to react faster? So in addition to the thiol exchanging fairly quickly, what's the difference between this carbon and that carbon? Right? It's primary, right? It's sort of like a primary nucleophile. It will allow us to effectively add in much easier because it's going to be a better nucleophile. That means it's going to be less restricted sterics that might involve and might come about based upon folding and so forth. And so what will happen is you will get, bless you, an exchange to the thioester. Okay, and now it effectively acts like an arm, and we'll bring it in, and effectively make that hand a bond. So now, while the amine has a difficult time attacking on its own, if it can be sort of shepherded in, right, by the thiol-based compound, now you're basically doing that through an intermolecular process. And the thermodynamics are that the amide is going to be more stable. So it's eventually, at the end of the day, a thermodynamically driven process where now what you have is your native bond. Okay? Pretty cool, right? Like, it works, again, quantitatively. It works selectively towards that sort of N-terminal cysteine. And the thing is that what would be the sort of downside of it, right? Is that you would need to have that amino acid there, right? And so this has opened things up in a major way. Like, it's a common enough amino acid. You would certainly have to build your synthesis around where that might be in the amino acid sequence, but it would at least allow you to get there. 1 and 2. Say that again? Yeah. Say that again? Oh, okay. Margot. I think it's not as, so I think the OH, so the question is nucleophilicity of an oxygen. I don't know, but I don't think so. I think there's something special about the sulfur. You can actually deprotonate and under certain, under slightly basic conditions, it will actually be anionic in nature as well, which you can't do with the OH. So I think this is in part due to the fact that you can, under slightly basic conditions, you'll actually be anionic form. So that's probably an important point to make. Okay. Now, what's interesting, what sort of people have taken from this is they say, okay, well, we need this specific amino acid. Can you perhaps do this with other groups? Yeah.
So the cysteine,
right.
do we have to pick a cysteine at all? Because wouldn't it find disulfide with another cysteine? I thought not when it does this sort of reference to another cysteine. Like if you're making a larger molecule,
Right.
wouldn't there be a problem with forming disulfide?
Oh, right. Yeah. So that's a good question. So the question was brought up, sulfur under especially oxidative conditions will rapidly form disulfide bonds. So the question basically came up, how do we deal with that? And yes, there are protecting groups. And there's orthogonal protecting groups. There's been a lot of thiol-based orthogonal protecting groups. So that you could build up a molecule where all the protecting groups for all the cysteines are 1, and then the one that you eventually want to do the native chemical ligation on has a different orthogonal protecting group. So you can deprotect this one in the presence of the others. And again, that would come in from the starting. You'd start that with the amino acid that you would have. So you'd start it with the fragment amino acids having one group, and then you would just substitute in the one that has a different protecting group to basically put on at the end. Okay, yeah?
So, basically, what we do is like an intermolecular attack, right?
Right.
What if your R1 and R2 groups are so large that it doesn't really allow you to turn around and do that?
Yeah. So the question that you're kind of asking is, are there limitations? And yeah, but it's been power enough. And again, when Tom Muir comes out here, he'll talk about this a little bit. I mean, they've been able to make enormous amino acids. So like anything, there are limitations, and in fact, those limitations inspire further developments. For example, and one of the ways that people have done this now is that they have taken, what if you don't want the cysteine? Right? Like, what if you want a different amino acid? Well, one of the things that people have developed is, it's known, in fact, that you can, and this comes down to protecting groups as well. If you have a free thiol, you can actually reduce off that thiol. Okay? So, if, say, for example, you have or I mean, we can even do it here, right? If you took this molecule and under specific conditions, I forget exactly what the conditions are, but it's sort of reductive conditions. what can happen is you can actually break that carbon-sulfur bond. And so if you don't have the cysteine in there, if you want to go to different groups, right? Now what you can basically do is you can get that methyl group, and that's, I always forget my amino acid, that's alanine, or I think alanine is nothing, I forget the different one. But anyways, that's another amino acid. So you could effectively get to this one, and you could have that somewhere in the sequence as well. So, and it turns out that people have developed routes to put thiols in other things, right? Like, let's say you wanted, say for example, phenylalanine. Well, people have made this, right? And so you can basically use phenylalanine, right? And when you reduce it off, wherever you want to put that linkage in, you can put phenylalanine. So this would sort of be, I forget who asked the question about the limitations, right? If it doesn't work at a specific peptide bond linkage, there may be another peptide bond linkage within there. Because certainly if you're restricted to having to do it at the cysteine, then you're at the sort of fate of the protein and all those other things. But if there's a different amino acid where you think that you might have a better shot doing it, then you might be certainly in better luck. So anyways, it's cool stuff. Again, this requires orthogonal protecting groups for thiols, because even if you want to reduce it off, you're going to want to make sure that all your other thiols are protected, right? And so you need to certainly deprotect the one in the presence of the other, and all these other things. And people have come up with really cool variations on this. Tom Muir being one of them, and have really sort of exploited this to sort of build molecules. Because certainly there are other ways, and you might learn in biochemistry other ways where you can certainly use, say, organisms, right, to generate the proteins and peptides for you. That's a very efficient way to do it, right? And that's probably, if you have a protein, you generally express, in the bacteria, get the bacteria to sort of excrete this protein, and then you purify the protein. And that's generally the way that you would want to do it. But there's a certain lack of control there that you would have in that type of context. That in building from the ground up you would have. A perfect example is my postdoc advisor. I considered talking about this, but I don't know. Yeah, why not? Sure. So my postdoc advisor, I'll just have to look up the structures because I'm not sure about them. But this kind of ties in sugars with amino acids. And so anyways, this is native chemical ligation. It's cool, it's powerful. Come to Tom Muir's talk next fall for the Friedman lecture. He'll be talking more about this stuff in terms of the developments that people have made. But this has really allowed people to actually make protein sequences. Now, what's the advantage over things like bacteria? One example would be my postdoc advisor, if I can get this to open. There's a class of molecules called advanced glycation end products. And one of the projects that Dave has that I think is really neat, he's interested in this class of molecules in general. And a friend of mine, a good friend of mine, who's now a professor down at LSU, published his sort of first paper on this stuff. Yeah? Huh? What? So,
how is it different from the regular amino acid
because it just takes place spontaneously. You mix a thiol with a thioester, and they'll just react together without really any really strong need to coax them. You don't need DCC. You don't need to generate all these urea byproducts. It's extremely high yielding. It allows you to make, again, if you're at 20, you're going to start having folding and so forth, so you want a better nucleophile that would bring it in. This is a better nucleophile that will help assist in this sort of forming the bond. If you cannot take a 20 amino acid sequence and another 20 amino acid sequence and couple them together using DCC, you're going to get a very low yielding process, and it's going to be highly, and then if you want to continue to do that over multiple sequences, you're just not going to get enough material to do anything. This is basically a quantitative process that you can do that works on even bigger proteins when there is this folding, and it effectively allows you to bring bigger sequences together. If you try to just do standard DCC coupling on these bigger sequences, you'd have to have all the different protecting groups protected. You don't necessarily need to have all the different protecting groups protected in this case. You can, but you don't need to because it's so specific and orthogonal to all the stuff that's out there. And again, it allows you to do chemistry that you could otherwise not do, in part because of this sort of better nucleophile for intermolecular that effectively directs ultimately the intra. The product's the same, but it doesn't. But you can't do what we did before. People have tried. You can't continue to build out. And even if you could, you'd start getting really low reaction yields. So what you need is a way to take 20 mers and 20 mers and couple them together to make 40 mers, right? And that's going to be much higher, right? Because if you think about the math that we did, say for example, can I see your calculator again? Can you go 99 to the 40th and then 99 to the 80th, and we'll see the difference.
To the 40th is 26.69, and to the 80th is 24.48.
Wait, really? That's it? To the 80th and to the 40th? No.
What time?
0.99.
Yeah. Okay. Well, anyways, okay, maybe if we went to 98% or something like that. But the point is that it certainly exacerbates, and if you have two, even if those were the numbers, if you take, the same thing, that's going to exacerbate itself even further as you start going off longer. Whereas if you just make one and you get a 50% yield, and you get the other and you get a 50% yield, and you go those together. Well, that's exactly what we were saying. But here's the advantage, right? Is that that when you do it based upon organism's mechanism, right? What you don't have when you base it upon an organism's mechanism is you don't necessarily have the control. And so you might say, oh, I can tune that into a DNA sequence, and I could make the plasmid, and I can put that in there, right? You still don't have control. For example, because what you would need to effectively do in that situation is, say, for example, you had an unnatural amino acid, right, that doesn't necessarily have a native code, something that encodes for it natively, right? You would then have to do a lot of work to generate a new code for that guy. And certainly people do that, and that's one strategy. But there's a lot more control, and a perfect example is this class of molecules called advanced glycation end products. And so what advanced glycation end products are, you know what? And again, it's not that there's not going to be specific situations where you would not want to do that. Again, that's probably still the go-to way to make enzymes, is exactly what you're talking about. But there is still a lack of control. There are still certain things that you can't do. And one of the great things that Tom Muir will often say in his talks is he'll say, that which I cannot build, I cannot understand, right? Like, if I can't build it from the foundation and ground up, I will never truly understand it. Now, let me just tell you guys really quickly about advanced glycation end products. So here's an example. So advanced glycation end products are effectively compounds that are formed from specific amino acid sequences along with sugars. So there's a process that's actually, the browning of toast actually takes place through this process. What you have here is, you can sort of see the hydroxyls that are remnants of the sugar. There's a mechanism that effectively will take amino acids and they'll actually be condensed within sugars. And there's a variety of these different compounds. And they've been implicated in a lot of different, see if I can find an image of a lot of these different ones. Right, so there's a lot of different versions of these. Right, so here's a table that's got a bunch of them. Oh, where'd you go? anyways, there's several different versions of these molecules, and they've been implicated in a lot of, they find that people that have certain diseases, for example, have high levels of these incorporated within the proteins in their systems. And so the sort of question is kind of like, what are these? How do we know what they are? And how do we know if, say, for example, a specific, is there a specific sequence where a specific age triggers a specific disease? Is it correlative? Is it something that when you get this specific, right? It's like cancer, right? Within cancer, like different mutations, some mutations, nothing will happen. Other mutations will lead to cancer. And so there's big work that's often done to try to understand what some of these mutations are that would lead to certain cancers. Within protein chemistry, this is a similar type of thing. They see these changes in peptides and protein sequences. They seem to be elevated in specific humans, and they don't really know what the roles of them might be. And one of the things that you might want to be able to do is actually synthesize these molecules with these specific sequences. And maybe there's a bunch. That's one of the problems, is oftentimes when you have these ages, they're all over the different peptides, and you can't really make them in a specific way. So one of the things that you could do is you could synthesize something like for example, this is an example of an age over here. So this is lysine, again, contensing with sugars and some other things, right? And what you get is this group over there. It may be found in a protein sequence. How would I put that specific group into a protein at a specific position? And how do I know that one specific position isn't different than another specific position? So one approach would be exactly like you're saying. Come up with some code within the DNA, right, that would encode this amino acid, right? That's not necessarily as easy said as it would be done, but it is certainly an option, and people do it a lot. It's a fairly standard technique. Another option that might be useful, though, would be if you could synthesize a molecule like this in the lab, make it, and then just make a peptide and put it at a different position, right? Now imagine you're in a situation where you have all these different proteins that would be there. You can imagine advantages to be able to make that change on 120 sequence unit, couple them all together, make the protein. Okay, now I want to put it at a different position, couple them together. Now I want it at both of them, couple it, put it together. So having that control is a complementary potential approach that could only be done if you can actually synthesize a peptide or a protein from the sort of starting point up. Now, in the case of Dave, my postdoc advisor, they were looking at it specifically in smaller peptides, but you could certainly imagine taking this to the next level, and I'm sure that he has in mind taking this to the next level in terms of, he's just the sort of starting point, but his vision is probably ultimately, on bigger molecules where these might be characterized. So again, I think that's the approach. Again, there's benefits and advantages to each of them, and I think, but having control, having absolute control, let's say there's a specific glycation pattern, right? Like when you express something in a bacteria, you might get glycated, you might end up getting glycation of the sugar that you want. You might not want that. It just happens to be because of that bacteria. I'm sure there's ways to knock that out, but it might be a problem. Well, here you don't have that. Or what if you want the glycation in a specific position? Well, again, you can sort of see where I'm going here. As you're sort of building up these things, you can potentially tune them in a way that you wouldn't be otherwise. So there's control in this that you might not have in biology. That make sense? So anyway, so these are ages. That just sort of brings up that point that sugars, and there's sort of interesting, there's this sort of thing called the Pomodori process. Did somebody ask me? Is that on? Oh, Maya's reaction. All right, so again, it'd be a really easy question to ask on, hang on. So again, the sort of Pomodori reaction is ways in which you can effectively begin to get sort of nitrogens that would be associated with amino acids, for example, within sugars, and then again, there's a lot of downstream processes that will then take you to do a lot of other, for example, cascade processes. I'm struggling to find an exact example. But anyway, if I can find something, otherwise bless you. I couldn't find any. Right, but again, here's sort of with lysine, right? Right, here's an example of it with lysine, right? So a lot of these sort of advanced glycation end products really start with reactions that put the sugars onto the nitrogens and then go through the process. So anyway, that's just to sort of follow up on that question that was asked. And again, there is potential. The other thing is where chemical ligation can be actually really key is with, for example, probe development, right? If you have, you want to attach a fluorescent probe, for example, to a protein because you want to follow that. Sometimes that's actually not native chemical ligation, that's just chemical ligation. And so these are just ways that you could, imagine doing similar types of chemistries to simply get, if you have, say, an N-terminal cysteine, you could modify that N-terminal cysteine very readily with, say, for example, some fluorescence based upon this process. So anyway, with that, I guess I'll let you guys go. So again, just as a reminder, I'm going to try to get this online again. Hopefully I can do it today. But I don't think I'm going to do it the way that I've done it in the past because I'm nervous that my computer will cease from existing. Like literally, I'm going to throw it out the window. But I'll try to get them up today. If not, it won't be up for a little while because I can't do it at home anymore.